potential nurses, potential Post-Utme candidates. I welcome you to the continuation of our lesson. And today, for the second part of our physics, we are continuing with vectors and scalar quantity. Vectors and scalar quantity. Welcome. We look at vectors and scalar quantities. All right. Let's put, scalar here. And let's put vector here. All right. We want to understand the difference between both. All right. It is said that scalar quantity has magnitude. There is magnitude. All right. But no direction. There is magnitude but no direction. So a scalar quantity is a physical quantity that has magnitude but no direction. What is magnitude? Like I said, magnitude is strength. All right. Strength or the extent of something. Okay, how far something can go. That's magnitude. All right. Okay, or trajectory. All right, these are words used instead of magnitude. All right, but no direction. Always use anywhere below face to remember scalar quantity. Anywhere below face. All right, anywhere below face. That's what I always tell my students, to remember what scalar quantity. No direction. All right. Example of scalar quantity. We have speed. All right. It has magnitude, but no direction. You just the speed. They go. It is straightforward. No direction. You can't say the vehicle is speeding towards east. No. The vehicle is speeding towards south. No. It has no direction, but it has magnitude. It has strength. It has trajectory. All right. We also have temperature. The same thing. No direction. All right. We have distance here. Distance. All right. So all these are scalar quantity. We also have magnetic. All right, magnetic flux. All right, and so on and so forth under scalar quantity. Okay, it is here that we still have mass. All right, and so on and so forth. Time is here. Energy. Okay, mass, time, energy. All right, all these are scalar quantity. No direction. You have energy. You have the energy. Your energy get direction? No. Time. Does time have a direction? No. It just continues to go. Time continues to work. The clock continues to tick. No direction. Does mass have a direction? No. The amount of matter contained by a substance. All right. Matter contained in a substance is known as matter. All right. Then looking at vector quantity, contrasting. All right. It has both magnitude. All right. A physical quantity that has both magnitude and direction. Both magnitude and direction. All right. It has both. All right. So looking at the examples here, we have force. We have displacement. What's the definition of displacement? The distance moved in a specific direction, or the change of the state of body with reference to a frame of reference, or with a frame of reference, or with a direction. We also have momentum here, acceleration, velocity. All right, momentum, acceleration. All right, we also have velocity. We can have magnetic flux density here. All these are what? Vector quantities. All right, so that's that for vector and scalar quantity. There is something we want to look at here. All right, the resultant of two vectors. All right, it can not necessarily be two vectors. It can be two or more vectors. Resultant of two or more vectors. All right, we are looking at the resultant of two or more vectors. So I want you to understand that anywhere you see resultant, okay, of two or more vectors, what does this mean? It means when you add two or more vectors, it gives you the same effect of a single vector. You add vector 1, vector is represented as force 1 plus force 2 plus force 3, for example, equal to a single vector. Okay. All right. So this is the resultant vector. Okay. You add two or more vector to give you a resultant vector. All right. And what is a resultant vector? A vector that gives you the same effect of the three or more vectors when added together. Three or more vectors that gives you the same effect as a single vector. All right. So these are three or more vectors, but when you add them together, they give you effect of the same vector. That is what? The resultant of two or more vectors. So this is the resultant. giving the same effect of 2 or more vector. It can be 2, F1 plus F2. All right. So there are methods by which we employ to determining the resultant of vectors. All right. We have basically 4 methods. Okay. Those are the most common methods. We are going to look at them one after the other. The first is the what? Methods. All right. Let's say methods. Methods. All right. To what? To determine resultant vector. Resolution of vector is different too. All right. So the first one is, let's say, A, parallelogram law. All right. Parallelogram law. This one is known as the what law? What is it known as? It's known as the what? The tail to tail. All right. The law states that when you align 2 vectors tail to tail, all right, or when you align 2 or more vectors tail to tail, what is the resultant? The diagonal. The diagonal is the resultant. All right. So the second one, which is B, we can also use another method called the triangle method. Okay. Triangle method or the triangle law. And what does the triangle law state? It states that when you add 2 vectors or 2 or more vectors, head to tail, all right, head to tail. What is the resultant vector? The resultant vector is the joining end, okay, the joining end or the closing side. All right, the closing side is the resultant vector. So let me illustrate this for you, the second one now, because this one is straightforward. All right, let's say this is vector 1, F, this is the tail, this is the head, this is vector 2, this is the tail, this is the head. You bring them tail to tail like this. What is the diagonal? This diagonal like this is the resultant vector. The diagonal is the resultant. All right, so let me explain the B. Okay, let me illustrate it. Let me put up an illustration here. All right, so illustrating B, we are going to quickly say, for example, we are using 2 vectors, F1, F2. It says what? The closing end, the triangle law. All right, see what we are going to do, like this and like this. All right, so this is the triangle law. You bring them together. All right, here is the closing end here, right? So this is the what? The resultant. All right, this is the what? The resultant. Definitely F3. All right, to be our resultant vector. All right, so the final one is C. Not necessarily the final one. We also have another one, but I will just name it for you. You don't really need to focus too much on that. It is called the analytical method. All right, the analytical method. And the analytical method is all about geometry. All right, it's all about geometry. Don't just stress yourself. Don't just stress yourself. Bother about the formula. This hardly comes out in College of Nursing Sciences entrance exam. So don't stress yourself too much. So let's quickly look at relative velocity. Relative velocity. All right. Like I taught before in our previous classes, anytime you see relative, just know that it's talking about looking at something or measuring something from a frame of reference. You are using something to measure another thing. So that's relative velocity for you. When you use something to measure another thing. All right. So for relative velocity, we have to understand what is known as frame of reference. All right. Frame of reference. All right. So this one is the frame of what? Reference. All right. What is a frame of reference? Frame of reference means something that you are using to measure another thing. Take, for example, you and I, we are running. All right. We are running home. How do you determine if I am ahead of you or if you are ahead of me? Is it not using me as a frame of reference? Using me to measure how fast you run or the distance you've covered? Yes. So let's say the end point where we are going to is our house. This is our house gate. All right. The gate of our house. All right. This is the what? The reference point. So this is a frame of reference. So we both are on a race to get to what? This place, which is the frame of reference. So who gets here first? We use this frame of reference to measure how far we have traveled or how far we ran. All right. And also measure how fast we ran, the speed too. So that is a frame of reference for you. So when we have 2 cars, now we are looking at relative velocity now, for example. All right. Relative velocity. For example, let's say we have 2 cars here. All right. Car 1 or car A and car B. This one is car B. All right. So to monitor the speed of this car or to monitor the velocity of this car, the 2 cars, how do we monitor the velocity? what we are going to use here is relative velocity. We are going to use a frame of reference. All right. So this one is the first car. This one is the second car. One is ahead of one. So how are you going to know if one is ahead of the other? Is it not by using the frame of reference? Relative to another. Measuring one relative to another. That is relative velocity. Anytime you see that relative in physics, just know that is measuring one with the what? With the target of the other. Okay. Using one to measure the other. All right. So relative also means comparing two. All right. Comparing two or more. When you compare two or more things, it's relative. So I can measure your temperature of Mr. A, and I measure temperature of Mr. B. Let's say the first reading I got 36 degrees Celsius. The second reading here for the Mr. B, I got 36.2 degrees Celsius. Okay. So if I am comparing the temperature now of both, I can therefore say the relative temperature of A and B is 36 plus 36.2. And that will give us equal to what? It gives us this plus this will give us 12. This plus this will give us 6. That's 72.2 degrees Celsius. So this one is the relative temperature. Okay, I hope you understood. So here now in physics, because we are looking at the physical, we are using one to measure the other. All right. So it's the same thing that we are going to do here. So when measuring relative velocity, if the two objects are moving towards the same direction, what do we do? Let's say for car A, it has a velocity of 10. Car B has a velocity of 12 meter per second. All right. So measuring the relative velocity, how do we do that? It's very easy now. So if they are on the same direction, they are moving towards the same direction. How do you measure? Let's say moving towards east. All right. Towards east. How do we measure? All right. To find the relative velocity is equal to, since they are moving on the same direction, you will have to minus. Okay. So you minus the velocity of the bigger from the smaller one, minus 10, equal to what? 2 meter per second. All right. So this one is the same direction. But if they are moving towards opposite direction, relative velocity will be what? Adding two of them. So you add 12 plus 10 gives you what? 22 meter per second. All right. So take note of similar direction and different direction, or the same direction or opposite direction. All right. Let's quickly look at resolution of vectors. The last one we dealt with was resultants of two or more vectors. Now let's look at resolution of vectors. All right. Resolution of vectors. Resolution of vectors. So resolution of vectors. So resolution of vectors is simple. It means solving vector problems. All right. Solving vector problems. All right. So how do we solve these vector problems? We solve it by splitting a vector into components along two perpendicular directions. All right. You split the vector. All right. Split the vector into how many components? Into two components or two parts. Okay. Along two perpendicular directions. So these two parts that you splitted it into, it should be along two perpendicular direction. What is perpendicular direction? Like this. So like this is perpendicular direction. All right. Remember perpendicular. Something that is perpendicular. Intercepting. All right. Intercepting. Perpendicular direction. Like this and like this. All right. So you split the vector into two components. You'll be having something like a crisscross kind of geometry. All right. All right. So let's say this is vector first vector, vector 1, and this is vector 2. All right. So that is resolution of vector for you. We use it to solve vector problems. As easy as ABCD. As easy as what? ABCD. For example, let me draw a vector diagram. Okay. Or a vector graph representing a vector. This one is y-axis. This one is x-axis. All right. Then I bring this out. Okay. Let me make this a little bit straight. All right. To avoid confusion. All right. This is s-axis. All right. And here is an angle. We put theta here. All right. So we have for the horizontal axis. If you are asked to look for or to resolve the vector on the horizontal axis, that's like this. Vertical like this. Horizontal like this. Horizontal axis is sine. All right. Then vertical axis is cos. Don't forget to. Then we now put our vector here first for the what? Vertical axis. We put our vector here first for the horizontal axis. All right. And this is the first. So you are going to be asked to find the vector, the first. Either you are asked to find for the vertical axis or you are asked to find for the what? Horizontal axis. or they can label this as force 1 and this as force 2 and tell you to look for force 1. What do? It's easy. If we are working on horizontal axis, for us to get the vector here, if we are working on this horizontal axis here, for example, the formula will be F sine theta. So this one will give us our force. Okay. So let's take, for example, here they give us a force of 10 Newton. Okay, that's this force here. Okay, this perpendicular force. So we are going to bring it down. We substitute 10 sine theta. What is theta? The angle. This is angle 90. Angle 90 divided by 2 is what? Angle 45. So 10 sine 45. You are going to times it. Okay, times sine 45 degree. All right. So when you do it, you determine sine 45. There is this thing we normally use to determine it very fast. All right. Number of finger below, square root of number of finger below over 2. It's very easy. So you put 90 degrees here, you put 60 degrees here, you put 45 degrees here, you put 30 degrees here, and you put 0 degrees here. So if we are looking for 45, for example, we are going to do square root of the number of fingers below over 2. That's how many number of finger below? 1 to 2. So we are going to say square root of 2 over 2. All right. So that's sine 45. All right. So that's that for that. So if we are asked to look for cos, for example, this one is the cos, or we are asked to look for the horizontal, the vertical axis. All right. So like I said before, when you are dealing with physics, any calculation relating to vertical axis, you normally use, I think there's a mix up here. There's a mix up. Okay. Vertical axis is sine, horizontal is cos. All right. Vertical axis is sine, horizontal is cos. So here we are going to replace this with cos. All right. So cos 45 degrees. All right. Times cos 45 degrees. All right. This times this one, root 2 over 2. All right. So this is likely 1 over 2. But, okay, this one is for sine. If you want to do cos, if you want to use this thing to determine cos, this one is for sine, Abi. Was it not sine we did just now? Yes, for sine. If you want to do cos, you will invert it. Instead of 0 to be here, 90 will not be here. It will not be 90, 60, you understand? 45, 30, and 0. For example, let me draw it here. All right, this is the arm. We're now going to put here 90 degrees, here 60 degrees, here 45 degrees, here 30 degrees, and here 0 degrees. It's the same thing. All right, it's the same thing. So you use your normal formula to get your cos. So immediately you get your cos, you substitute and you solve. There's another way of determining this sine 60 or cos 45, cos 30 using SOHCAHTOA. All right, all these are basic mathematics. SOHCAHTOA. All right, SOHCAHTOA. All right, you can also use this one, which is this one, opposite over hypotenuse. Okay, sine equal to what? Opposite over hypotenuse. All right, then we have cos. Cos equal to adjacent over hypotenuse. It's very easy. Then this one is for tan, opposite over adjacent. So once you just draw your angle, all this one is basic, this thing. You can easily determine it, all right? Or you cut it half from one side, all right? So still on this resolution of vector, like I said, when you have horizontal, if you are working on horizontal, that's like this, you use cos. If you are working on vertical, you use sine. That is the same thing anywhere in physics. If you are asked to calculate motion of blah, 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 in a plane surface when an object is submerged vertically at angle 90 and so on and so forth, is sine that you are going to use, provided it's vertically inclined. All right. When you hear horizontally inclined, that's when you are going to use cos. All right. Use cos. So under this resolution of this vector, okay, we have methods that we use to, resolve vectors, and they are graphical methods. All right. Graphical method. Just like the one we just did. But let's explore other graphical methods. All right. This one we just did is the triangle method. Okay. The triangle method. All right. That's what we just used. All right. So we also have the parallelogram, using the parallelogram law, the normal parallelogram that we learned just now. All right. Which is what? T to T. T to T. We also have the triangle law, which is what we just did. Okay. The triangle law, which is what? Head to what? T. All right. Then we have the final one, which is polygon law. Hope you remember what the resultant is, right? For the polygon law, the resultant is equal to 0. Resultant equal to 0. This one, the diagonal is the resultant. This one, the closing end is the resultant. We already discussed that before. So you can see vector diagram, resolution of vector in various ways. And they ask you to resolve vectors. For example, let me draw a graph. No need for this one. You don't need it. Okay? You don't need it. Now, JUPEB, they set on those kind of questions. You don't need it. If you need to understand more of it, just go through the lesson notes. But I don't think you need it. It's not something you need, okay? It's not something you need. So let's move over to displacement. Like I defined before, I said displacement is the distance moved in a specific direction. All right? Is the distance moved in a specific direction. All right? It's a vector quantity. So let's say displacement. All right. So this is displacement. And in displacement, where the change in position started is called the initial position. You know, it's towards a specific direction, right? This is the direction, all right? And this is what, where it ended, all right? So displacement ended here. The object has been displaced from here to here, or from point A to point B, all right? And this place will now be called the final what? The final position in displacement. So they can give you a length of 2 meters due east, and they give you 5, or let's say they give you 4 meters due west, for example. All right. So they now ask you, what is the displacement? It's very common. This thing is very easy. Just apply Pythagorean theory. All right. Pythagorean theorem to solve. Pythagorean theorem where a square plus b square is equal to c squared. Okay, so if you bring this into, you substitute, a square will be the first one, which is 2 raised to power 2 plus 4 to the power of 2, which is equal to, we do this. So when we do this, we get 4. 4 plus, 4 times 4 is 16. All right. So this plus this 20, we're now going to be left with 20. Remember, how do we finalize the answer? Square root of 20. We get the answer. That's the displacement. So 2 should be our answer. Displacement due east, right? Displacement due east. But in the question here, displacement from 2 meters to this. Okay, let's see. Let me quickly do that to see the answer we are going to get. All right. And we got, okay, square root of 20. I want to be very sure. Okay, 4.47. All right, 4.47. That's 4.5. Approximately 4.5. All right, so that's the displacement. All right. So if we had, maybe we had, let's look at what we have here. Let me look at the example we have here. The question here is walking 8 meters due east, then 6 meters due west. Okay, since it's from east to west, okay, what are we going to do there? So we are going to have 8, this one, then you are now going to use minus. Okay, so you minus to get the answer. So because it's from east to west, okay, from east to west, and the answer is now due east, according to the question we have here, due east. All right, we will have to minus. Okay, so let's say 8 squared plus 6 squared, okay, minus 6 squared. All right, this should be equal to 64 plus 36, right, minus 36. That should give us 64. Wait, this times this times this, and this. Okay, that should give us 28, right? That should give us 28. Then we will now have to calculate the other one. Okay, so we are now going to be left with 3. Then we will do the square root of that. We get 5 of 28. 5 minus 3 equal to 2. So it should be 2 meters. But this question is quite complex. They hardly said this kind of question. Once you just see any question from displacement like this, and you are having just 2 distance, just apply Pythagorean theorem and get your answer. All right? Apply Pythagorean theorem and get your answer. Very easy. Right. Let's move over to the next. We don't have to spend much time on displacement. In your College of Nursing Sciences entrances, and what they are likely going to ask you here is just what is the SI unit of displacement, or they will define displacement and ask you among the options, pick the correct option. All right. Pick the correct option. We understand that distance is the what? We already spoke about frame of reference, and we understand that distance is the space between 2 points, right? So this is distance, the space between 2 points. All right. And we already spoke about frame of reference, and I told you that frame of reference is something that you use to measure another thing. All right. Something that you use to compare another thing. All right. And frame of reference, we have two types of frame of reference. We have the stationary frame of reference, stationary frame of reference. Then we have the moving. Number 2, we have the moving frame of reference. All right. So what is the difference? Let's say we are looking at stationary now. We have car A and car B. All right. They are on something, a competition called car race, car A, car B. All right. And what marks the end of the car race? It's a gate. This is the gate. So the first car to get to this gate becomes the winner, right? Yes. So what's the frame of reference? The gate, right? But what kind of frame of reference is the gate? The type of frame of reference that this gate is what? Stationary, because it's what? Static. It doesn't move. So it's a stationary frame of reference. So let's take for another example, example 2, these two cars now, they are moving on the road. All right, car A and car B. All right. As they move on the road, we want to observe their relative velocity. All right. What is their relative velocity? How do you know their relative velocity? If you already know the relative velocity of one, you can use that one's relative velocity to compare with the other one, right? To observe if this one has a faster velocity, if this one has a higher velocity or a lower velocity. All right. So we are now using something that is moving as a frame of reference, either this one or this one, either car A or car B. So since we are using something that is moving as a frame of reference, that makes it what? A moving frame of reference. As simple as that. When we measure, in our last class, we treated measurement. All right. When we measure, especially when we are reading, instruments like vernal calipers and micrometer screw gauge, of which I'm going to teach you how to read the vernal caliper and how to read the micrometer screw gauge right now. There is the error margin we observe. All right. For vernal caliper, because for vernal caliper, for meter rule, let's start with meter rule. The error margin is usually 2 meters. I mean 1 meter. Okay. 1 meter is it 1 meter or 1 millimeter? It's 1 millimeter. 1 millimeter is the error margin for meter rule. Therefore, micrometer screw, the error margin is 0.01 millimeter. All right. Then for vernier calipers, error margin is 0.01 centimeters. 0.01 centimeter. All right. So we observe this because of what? Zero error. Okay. To get accurate reading. So this is based on the accuracy of the readings we are taking. Now let's look at how to read a vernier caliper. All right. Vernier caliper. So let's say this is the vernier caliper. Remember, the bigger scale is known as the main scale. All right. While the smaller scale is known as the what? Usually below is known as the what? Vernier scale. So how do we read a vernier caliper? It's very easy. Okay. Just read the main scale, read the vernier scale, add the two readings together, and you get your answer. But there is a step to it. Okay. So let's say, for example, we have 1, 2, 3, 4. This one is number 2. 1, 2, 3, 4. This one is number 3. That's 3 centimeter. You know the scale is in centimeter. Okay. Then 1, 2, 3, 4. This one is what? 4. All right. And so on and so forth. Let's now say what you have to look out for when you want to read your vernier scale is the point of coincidence. All right. Let's say this is the point of coincidence. And how do you know the point of coincidence, or what is the point of coincidence, or what is the point of alignment? It can be called point of coincidence or point of alignment. It's the point at which one of these pointer here, okay, one of these points here enters the vernier scale from the main scale. It connects from the main scale to the vernier scale on a straight line, angle 90 like this. Okay, there's no misalignment. That one at that point that it aligns from the main scale to the vernier scale at angle 90. That's what you are going to look for. But this is significant when you want to read the vernier scale. All right. First of all, we are going to take main scale reading first. Okay. So this is, let's say this is the vernier scale. 1, okay, 1, 1, 2, 3, 4. Let's say this is 1. Okay. Then this one, 1, 2. This one is point of alignment 2, 3, 4, 5. Let's say this is 2. All right, in centimeter. So what we usually do is that to read the main scale, that's the first thing you do. So we are going to put it down here. Main scale reading, MS reading equal to, since here is 2, just count from, it's just the value that the vernier scale starts from. That is the main scale reading. Here is where the vernier scale starts from, right? So it's 2.1, Abi, 2.1. This is 2. This is 0.1, Abi. So we put it there, 2.1 centimeter. All right. So when we want to read the vernier scale, this is where we are going to observe error. All right, vernier scale reading, we are going to observe this 0 error here. All right, anything we get, we are going to add it to this 0 error here. All right, 0.01 centimeter. All right, so at this point of coincidence, that's where we are going to what? We are going to get our reading from. So we are going to count and stop there. That's the reading we are picking. So this is 1. Since this is 1, this is 1.1, this is 1.2. So at this point, okay, at the point of alignment is 1.2. So we are not going to have 1.2. We are not going to have 1.2. All right, plus this, plus 0.01 equal to what? This gives us 1.21 centimeter. So we add our two readings to get the answer. 2.1 plus 1.2 centimeter equal to what? This will give us 3, and this will give us, okay, 2.21. All right, 2.21 centimeter. This will give us 3, and this will give us 3. So we get 3.31 centimeters. So this is our final reading for this vernier caliper. All right, as easy as that. So let's quickly look at how to read a micrometer screw gauge. Trust me, it's very easy. It's the same thing, just the same way you read vernier caliper. It's the same way you read micrometer screw gauge. Okay, it's the same way. Just that the name of the scale is called Timbul scale in a micrometer screw gauge. Instead of vernier scale, it is called Timbul scale. All right, that part is called Timbul scale. All right, so we are going to learn how to. First of all, we have to draw the micrometer screw gauge. So this is the micrometer screw gauge. Let's say this is the Timbul scale. All right, this is usually called the Timbul. All right, the Timbul scale. Let's say we have 1, 2, 3, 4, 5. Let's say this is 20. 1, 2, 3, 4, 5. Let's say this is 25. All right. So this one is not the main scale. Usually the bigger scale, like I always see. All right. Then you have something like this. This, something like this. That's how it always appear like this. All right. So let's say from here we have 2. Here is 3, or here is 2.5, 3. Here is 3.5. Here is 4. Here is 4.5. Here is 5. Here is 5.5. Here is 6. All right. So 6. So is this up to half? We are just going to give it 6.5. All right. So reading the main scale is the same pattern. Just look at the visible number, the most visible part on the main scale. This is the only visible part of the main scale here, and it ends in 6 point something. Okay, so let's just give it 6.5. That's 6.5. Okay, because between 5 and 6 is half. So between 6 and the next number will be half. Let's just give it 6.5. So main scale reading is equal to 6.5 millimeters, right? So when you want to read the Timbul scale, is when you will not observe the 0 error. Remember, it's in millimeter for micrometer screw gauge. All right. So for Timbul scale equal to, how do we read the Timbul scale? Where it touches, the point that it touches in the Timbul scale, this straight line here, where it aligns with, okay, where it aligns with. Here, you might not see straight coincidence or straight alignment like in vernier caliper, all right, but just look at the point where it points at, where this straight line points at on the Timbul scale, all right, so it points directly to 20, all right, look at it, 20 millimeter, so 20 millimeter. Then we add our what? Our error plus error margin 0.01. Remember, it's in millimeter. This gives us what? 20.01 equal to 20.01 millimeter. What do? We add both, right? 6.5 plus 20.01 millimeter. That gives us what? 26.01 millimeter. This is the final reading of this micrometer screw gauge. As easy as that. So you do yourself a favor, go and read more micrometer screw gauge. All right? Read how to read them. Just search online, search on Google. You see micrometer screw gauge. So you have different parts of the vernier caliper and different parts of the micrometer screw gauge. Like, let's look at the vernier caliper. In the vernier caliper, you have a part called the jaw. All right. That jaw is used to what? to, to hold on to where it's to be measured. All right. That's where you use to attach where it's going to be measured. Okay. We have two types of jaw. We have the outer jaw and the inner. Outer is used to measure outer diameter. Let's say you want to measure the diameter of a cylinder from here to here. The inner one is the one used to measure inner diameter. Let's say you want to measure the length of this inner part of the cylinder. All right. So it also has another part called the main scale. We already talked about that, the vernier scale. It has a part called screw clamp. It is this screw clamp that you use to adjust the jaw. Then it has another part called the stem. The stem is used to measure depth. All right. Depth. Maybe you want to measure the depth of this cylinder. Just put the stem of the vernier caliper and check the reading on the main scale, and you get the reading in in centimeter. All right. That's that for reading vernier caliper. Let's quickly enter motion. Let's quickly do motion. 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 Motion is a movement of an object. Okay. A movement of an object. Change in position of an object. All right. Change in what position? Change in position of an object. All right. That's motion. What brings about motion is what? Force. Caused by what? By force. All right. Okay. The force that is responsible for placing a body at rest, especially when two surfaces are in contact. Okay. When there is a frictional force. All right. For example, I'm standing here. The force that's responsible for me to stand still here, stationary, is called limiting force. All right. Limiting force is the force that limits me from moving, that keeps me in a stationary position. All right. So if once this limiting force is broken, motion is induced. All right. Immediately you break this limiting force, motion is induced. Let's say the limiting force is 25 Newton. Okay. For you to break this limiting force and bring about motion, okay, you are going to bring a force, or you are going to introduce a force to the body or to the system that is greater than 25 Newton. Let's say 25.5 Newton. Then you can start noticing some motion. 25.6, 26, 26 Newton, and so on and so forth. Immediately you increase it past the limiting force. All right. Motion is induced. And we have various types of motion, which we are going to look at right now. All right. We have oscillatory motion. The first one is oscillatory motion. Number one, oscillatory motion. All right. Oscillatory motion, which is what? To and fro, right? To and fro. To and fro, or back and forth motion. All right. This is oscillation. For example, movement like this from right to left. All right. All right. So this one is to and fro. It goes like this and it returns. So we are now going to have something like this and like this. So it goes like this, continues to what? To return, like this, or to and fro. To and fro can be like this, the horizontal to and fro, or the vertical to and fro. Or it can be jangilova, the one you do, or a simple pendulum. This is a pendulum bob, for example. This is the mean position. All right. Then it oscillates. At a point it will be here. At a point it will be here. So it moves like this, pendulum bob. All right. So that's oscillatory motion. Let's look at the second type of motion. Okay. This second motion, we are going to look at translational motion. Translational motion is easy now. It means it can also be called linear motion. Motion in a straight line. From here to here. When I walk from here to here, this is translational motion. It's in a straight line. All right. Another example is when a woman is pushing her baby during labor. Another example is a car moving on the road. That's what translational motion, from point A to point B. In a straight line. Always remember that. Number 3, we have rotational motion. Rotational / spin motion. Both of them are different. We are going to understand their differences. All right. For rotational motion, what is important here is the axis. In rotational motion, the axis is part. Okay. The axis is not part. The axis is not part of the object in motion. Okay. For example, the Earth rotation. Okay. So the Earth rotates around the sun. All right. So let's say this is the sun. Sun. This is the earth. So the earth rotates around the sun. You see earth here, you see earth here, you see earth here. It rotates around the sun. All right. Okay. So it's an orbiting when an object orbits around a fixed point or around a fixed axis. All right. But the axis is not on the object in motion. Okay. Around an axis. All right. So an object circles around an axis. Okay. And the axis is not part of the object. That's rotational motion. Then for spin motion, the axis belongs to the object. The axis is part of the object in motion. For example, you have a wheel, a car wheel like this. This is the what? The axis. Okay, this is the axis. So it rotates about what? This axis. The axis is part of the wheel. Okay, the axis is part of the wheel. Another one is when the earth spins. Okay, because as the earth rotates around the sun, it also spins. Okay, this one is the sun. This is the earth. This is rotation. But as the earth rotates, it spins like this. As the earth rotates, it spins on its own axis as it rotates about the earth. So one spin is usually equal to what? 1 year. Is it 1 year? 1 day. All right. Then one rotation is usually equal to 1 year. All right. So that's that for that. Understand that. All right. We have the final type of motion here, which is random motion, which is known as zigzag movement, right? Like this. Okay. For example, fly. When fly, they fly. Number 4, random. Random motion, also known as zigzag motion or irregular motion. I say, for example, the flight of a fly, or another example, the movement of gas molecule. All right, zigzag motion. Another example again is the movement of a woman in a crowded market. All right, you know when you are in a crowded market, you can't move in a straight line now. If you pass like this, you are just trying to look for the part that is less congested so that you can move. So if you go like this, you go like this, you go like this. So that's what? That's random motion. Now, let's quickly understand the law of motion. After law of motion, we quickly get into impulse, then the equation of motion. Law of motion, impulse, and the equation of what? Motion. The law of motion has 3 laws. The first law of motion states that, okay, that a body will continue to remain at rest. A body will continue to remain at rest, okay, unless a force acts on it. That force can that be internal or external force. All right. So I will continue to remain at rest unless a force acts on me. All right. And this expresses is also known as the law of inertia. Okay. Law of what? Inertia. All right. And what is inertia? Inertia is the resisting force. It's a force that keeps a body at rest. Inertia is a force that keeps a body at rest. So when you break inertia, the Newton's first law of motion is complete. All right. The Newton's first law of motion is complete when you break inertia, that limiting force that keeps that body at rest. All right. So mass is said to be, mass is equal to the measure of inertia. So inertia is equal to matter. All right. Summation of what? Matter. All right. That's what? Inertia. All right. So understand this. Let's quickly look at the second law of motion. The Newton's second law of motion states that the change of momentum of a body is P represents momentum. Change of momentum of a body is equal to what? The external force. Okay. It's equal to the external force and takes part in the direction of the force. Takes part in the direction of the force. The change of rate of momentum of a body is equal to the external force and takes part in the direction of the force. So, the force you apply to a body is going to determine the momentum of the body. So, if my momentum is this, the product of my mass and my velocity is this, then you apply a little more force to me, you push me small, like this, it's going to increase my momentum. So, it is the force that you add, okay, the force that you impose on me that is going to what? Determine my momentum. Equal force. The force you impose on me commensurates my momentum. You are still going to get the same effect to the momentum. So the force applied is equal to what? The momentum. And take part in the direction of the force. I can't be walking like this and you push me like this to this direction. You push me to this direction. No, I will now fall to this direction. No, I will fall to this direction. That momentum must take part, okay, in the direction of the force. All right. So usually, okay, let's just leave that. Let's go to the third law of Newton's third law of motion. All right. Let me wipe. The Newton's third law of motion. Newton's third law of motion. It states that all action is equal to an opposite reaction. All action equal to what? Opposite what? Reaction. Or to every action, there is an opposite reaction. Okay? So if I hold a gun now and I fire a gun from here, immediately the bullet leaves the, the nozzle of the gun. I am going to feel that recoiling effect of the gun. Okay? Which is what? An equal and opposite force. Opposite means it's going in opposite direction. An equal and opposite force. Okay? Towards me. Like this. Alright? Another one again. The application of this Newton's third law is also in jet engines. Alright? Jet engines. How does it work? Let's say this is a jet. Okay? This is the combustion chamber of the jet. And here is the big exhaust. So immediately gas is burnt here at a very high pressure. The gas evolves through the exhaust. And as the gas pushes backward, the recoiling force, opposite and equal force, pushes the jet forward and further into space. That's how the jet works. All right. That's that for that. And we already said that momentum, or P, is equal to the product of a body's mass times velocity. So P equal to m.v. All right. The product of body mass and velocity. Okay. The impulse of force is the instantaneous response of a body to the force that acts on it. The instantaneous response of a body to the force that acts on it. That's impulse for you. Impulse. You slap me now, I quickly respond. You push me, the person responds. There's change in momentum. That is what? Impulse. Alright? And impulse, which is J, is equal to force dot time. Force times time. Alright? This is impulse. So, because it's force times time, the SI unit will be Newton second. Right? Newton second. Alright? Then, we have to also note that impulse, J, is equal to change in momentum. Alright? So, take for example, you are asked to find the change in momentum of a body. Okay? But in your parameter, the parameters given to you in the question are force. They gave you 20 Newton and they gave you 1 second. They told you to find the change in momentum. Change in momentum, question mark. And you know that the formula of momentum is P is equal to mass times velocity. Mass and velocity. You need mass and velocity. So how are you going to solve? When here, you were given only force and time. You see? So if you don't know that impulse is equal to change in momentum, you will not know what to do here. So because they are equal, this is equal to this. You can use this to get this. If you get this, you already have this. So therefore, since impulse is equal to change in momentum, and we are asked to find the change in momentum, all right, we are going to calculate impulse, which is what? J equal to 20 times 1. All right? Force times time, which will give us what? 20. All right? Newton second. So this is the what? The change in momentum. All right? So let's quickly look at the conservation of linear momentum. What is the meaning of conservation of linear momentum? All right? It has a law. Okay? In the absence of external forces, total momentum of system remains constant. Anytime you hear conservation, just know that nothing is going to waste. Everything is going to be converted. Okay? Nothing is going to waste. Just like the law of conservation of matter, the law of conservation of energy. Nothing is going to be wasted. Nothing is going to be wasted. All right? Nothing is going to be wasted. And nothing is going to be created. All right? Momentum will never be created and it shall never be what? Wasted. That's the law of conservation of momentum. Momentum of the system remains constant. As simple as that. A, B, C, D. So, if we are looking for the conservation, we are asked question to calculate conservation of momentum, linear momentum between two carts. Let's say cart A or body A and body B. All right? Two bodies. Okay? This is the formula that you are going to apply. It's just momentum times initial velocity and momentum times final velocity. You do the plus and you do the times for initial and final velocity. So if you want to write the formula now, it looks long, lengthy, but it's very easy. So you are going to write M1, which is momentum, mass 1 times, or you just write U1. Okay? Then you now do it plus M2, okay, u2. Initial mass 1 and initial velocity. Mass 2 final velocity. Then you are now going to write equal to what you now do for the other side. Okay, and this one we are going to do it for final velocity. We have done for initial velocity and we do for final velocity. So m1 v1 plus m2 v2. So this is the formula for conservation of linear momentum. All right. There is also another formula used. Okay, but you can use this one. Okay, depending on the parameters you are giving. Any parameter that you are not giving, just leave it inside the, inside your calculation. Then later you collect live terms and you eliminate them. We have this one, m1 u1 plus v1 m1. Depending on what you are, if you see, for example, you are asked to solve and you were given only initial velocity. Okay, maybe you are given initial velocity 1 and you are told to find the second velocity. You are given velocity 1 and you are told to find the second velocity. You can just use this one. Okay, u2. Then bracket close, you put times v. Okay, like this. Or you can just do m1. Okay, u1 plus m1 v1. Okay, so this one we are working on v. U. Okay, so depending on what you are the one, you are just going to use this to derive the formula that you are going to use to solve. All right, depending on the nature of the question. But one thing I must say to you is that if you use this formula like this, you are going to get any answer. Just substitute what you were given and collect live terms. You get your answer. No need to be stressing yourself and be deriving formula. That one is even waste of time. If you just know this general formula like this, which is very easy, you've gotten your answer now. Nothing did there. All right. So we have to understand that force is that which change a body state of rest. All right, changes a body state of rest. Yes, that's for force. And force can either come as a what? As a push or what? Pull. And we have force fields. These are the type of force. We have force field, number 1, force field, and we have number 2, we have contact force. Contact force. What is the difference between these two forces? This one requires contact. That's why it's called contact force. This one does not require contact. Under the contact force, we have frictional force. Friction. We have reaction force, or the one they call normal reaction. Reaction or normal reaction. Then 3, we have surface tension. All right, and you know that under this friction here we still have viscosity. That's if it's in a liquid. Okay, viscosity. All right, then for the what? For the force field does not require contact. Okay, it does not require contact for you to experience a force field. Example of force field, we have 1, which is gravitational pull. Gravitational pull. All right, when do we expect gravitational pull? When an object is decelerating. Okay, dropping from the earth. Okay, when it's ascending, it's going against what? Gravitational pull. All right, it gets to a point when the gravitational force is greater than the force exerted on the object or on the body. It gets to that point that immediately the gravitational force is greater than it, the object starts what? Dropping, and that is as a result of what? Gravitational pull. All right, so we have another force field. We have 2 more. We have a magnetic field. We have electric field. All right, magnetic and electric field. So these are force fields. All right, so what is a magnetic field? An area where the attraction and repulsion of a magnet is what? Felt. All right, what is an electric field? An area where the attraction and repulsion of charge is felt. And you know that electric field and magnetic field can come together to form something called a phenomenon called electromagnetic field. Okay, which is magnetic field plus electric field, or when electric field induces a magnetic field. All right, that's where you see you have an electric wire here. Okay. And here you have a cup of water. A cup of water here. And there's an electric charge in this wire. And someone holds this metal cup of water. And that person noticed an electric shock, a transfer of electric charge to this cup. But yet, there is no contact, no touch. Yes, it happens as a result of electromagnetic field formed. Alright? The electro ends here. The electro forms what? Magnetic field that travels from this wire to the metal cup and transfer charge. Alright? Through the what? The magnetic field. Alright. Now, let's quickly look at the equations of motion. Alright? The equations of motion. So do not forget that when calculating conservation of momentum, when you want to use the conservation of momentum formula, this is what the questions usually look like. They will ask you, you will see something like before collision and after collision. Okay, you must see something like this in the question. All right. Either you see before collision or after collision in the question. So that's how you are going to know. You are going to be given mass 1, mass 2, velocity 1, velocity 2. Okay. Like a question here, they gave us 2 kg as M1. Okay. They gave us 3 kg as M2. M2 equal to 3 kg. Then they give us U1. He said each other with a speed of, that's U1 equal to 4 meter per second. Then U2 equal to 2 meter per second. And they ask us what is their common velocity after collision. They are asking us what is their common velocity after collision. It's easy. Just in that formula, just substitute this, collect like terms, and you get your answer. Substitute this into the formula, collect like terms, you get your answer. As simple as that. We are not teaching basic mathematics right now. We have no much time for that, all right? We want to look at the equation of motion. Okay? The equation of motion. And after this, we reserve the next class for the interpretation of distance time graph and velocity time graph. All right. So looking at the equation of motion, acceleration, equation of motion, or the one they call accelerated motion. Okay, acceleration. Because when we are calculating deceleration, something is going to change, which is the sign. Abi, for acceleration, use plus, deceleration, use minus. That's the difference. So the first equation of motion, first, we are having our what? Our V is equal to U plus what? 80. No. V is equal to U plus 80. Yes, that's correct. All right. Where V is what? This V is initial velocity. V equal to initial velocity. All right. Then U, V is equal to final velocity. Let's just put it U here, equal to final velocity. V equal to initial velocity. V equal to final velocity. All right. Then A is equal to acceleration. Then T equal to our what? Our time. All right. So this is the first law of motion. Corresponds with the first law. The first equation of motion corresponds with the what? The first law. All right. So let's look at the second equation of motion. Remember what I said? Or let me write it out again and quickly explain that. V is equal to U plus 80. This is for accelerated motion. When we are calculating deceleration, for example, we are going to change this plus to what? Minus. All right. That's the difference. So the second equation of motion, this is the first The second equation of motion is S is equal to ut plus 1 over 2, which is half at raised to power 2. All right. We already spoke about their components, what they all represent, all these, their coefficients. All right. We've already spoke about that. S here stands for what? Acceleration. All right. And I said if you are calculating deceleration or decelerated motion, you use minus instead of plus. That's the difference. Then the third and final equation of motion is v squared equal to u squared minus 2as. But since we are calculating accelerated motion, we put plus. If you are calculating decelerated motion or deceleration, we use minus. Just like that. All right. So these three equations of motion, you can use it anywhere in physics. When you are doing any calculation related to motion, provided there is motion, there is change in position, you can use this. They ask you, even in projectile, they ask you, it's not even a must that you will just put all the formulas of projectile in your head. They can ask you like, what's the time of flight? Provided you have time here, you can use this law of motion to solve it. Okay, all you have to do is to just make subject of formula, do a little small derivation with your small mathematical knowledge, and you come up with the formula and you solve. Or sometimes you can just solve it like this. You substitute into the formula like this, then you collect like terms, and you get your answer. But since you are doing, you are using an indirect method, it's going to be better you make what you are looking for the subject of the formula, all right, before solving. Because sometimes, not all the time that this direct substitution work, okay, especially when you are using an indirect formula or you are using an indirect method to solve. All right. So, like I said before, you can use this to do any calculation relating to motion in any topic in physics. All right. For example, when you want to apply these formulas to whatever you are solving in physics, how do you pick from the three? Which do you choose? It's very simple. That's why before you start solving, look at your parameters. What were you given to solve with? All right. For example, you are given, you were asked to find distance. All right. This S stands for distance. S is equal to distance. Okay. Remember that this S also signifies what? Height. All right. So in a question that they gave you distance as height, okay, it was called height in the question. You can use this. You can use this second equation of motion to solve. This is what you are looking for, height. You just turn this one to height and you solve. That's it. So let's say you were asked to find distance and you were given initial velocity, you were given time, and so on and so forth, and you were given acceleration. This should be the best formula to apply. You can't use this one because here you don't have distance as the value. You understand? So depending on what you were given to solve, all you have to do is to write out the three equations and look at the one that is going to be the best fit for whatever you intend to solve for. All right, or whatever you are asked to solve for. Write them out. Look at the best fit. Ensure that all your parameters are in the equation, and also the value, which is this one or this one, the value is what you were asked to find. So let's quickly brush into acceleration due to gravity. All right. This one that is distance, that I told you that is distance. Let me write it out. S is equal to what? Height. S is equal to distance. S can also be referred to as displacement too. All right. So take note of that. Okay. So let's quickly brush through acceleration due to gravity. It's very easy. Remember that acceleration due to gravity is 10 meter per second square, or it can be given as 9.8 meter per second square. Okay, either this or this, either 10 meter per second square or 9.8 meter per second square. Just look at the one that you were given in the question. It can give you any, but if you were not given any, just use 10. Okay, I think 10 is the standard. But if when you are given a question to solve and you see 9.8, they gave you take acceleration due to gravity 9.8 meter per second. Don't go and be using 10. Use the 9.8 to solve. All right. Normally you are going to get close answer. All right. The answer is going to be close because the difference is just 0.2. But for you to get the specific answer, the correct answer as indicated in the options, just use what you were told to solve with. But peradventure, you were not given acceleration due to gravity in the question. All you have to do, use the standard one, which is 10. Okay, the 9.8 is also standard, but 10 is what commonly used. All right. So when we are solving for acceleration due to gravity, it's still the same, these three equations of motion we use. All you have to do is just that this place that you have acceleration, just put G there. That's acceleration due to gravity. Very easy. So this one, we are now going to have V is equal to U plus GT, right? The second one is equal to S equal to UT plus half GT squared. Abi? Then the final one, V squared equal to U squared plus or minus what? 2GS. So this is acceleration due to gravity. So when gravity is involved in the question, all right, you use acceleration due to gravity formula to solve. Okay, when it involves an object dropping down, or an object ascended and the object is dropping down, you use acceleration due to gravity. They normally tell you take acceleration due to gravity. So you use acceleration due to gravity. You change the A's to what? G. Thank you so much for taking this class. I will see you all